All right, let's go ahead and take a look at example 3. Example 3, we are going to analyze the critical points using the second derivative test. So unlike the previous example where we went ahead and analyzed them using the first derivative test. So here, we'll go ahead and first find our critical points. So the derivative here will be 2 minus 2x times the second function left alone plus the first function left alone times the derivative of e to the x, which is itself. Then, if we simplify this, we will get 2 minus x squared, because the 2x's cancel, e to the x. This exists on its domain, on the domain of f. So then the only way we get a critical point is if this whole expression equals 0. And now e to the x is always positive. So that means that this term here never equals 0. So if this term never equals 0, the only way this product of two things equals 0 is if this term equals 0. So this is true if and only if 2 minus x squared equals 0, which does happen when x is equal to plus or minus the square root of 2. So plus or minus root 2 are critical points. Let's take the second derivative. So the second derivative of this function, skipping some simplifications here, this is 2 minus 2x minus x squared, e to the x. In my written notes, I go through more of the steps, but here, these videos are getting a little long, so let's go ahead and skip a few steps. So there's the second derivative, all nice and neatly polished and simplified. So now we want to go ahead and see if we can evaluate this at our two endpoints. So one thing that you can go ahead and plug in these two things separately, or you can sort of do them simultaneously, which is what I did. So I'm going to plug them both in simultaneously. So I'm going to keep a plus and a minus on here. So in this case, I'll have 2 minus 2 times our positive negative square root minus our positive negative square root squared times e to the plus or minus root 2. This might look strange, but it's a quick, convenient way of breaking up two mundane, very similar calculations to save yourself time. So notice here that if I plug in positive root 2, this term here, positive root 2, gets multiplied by a negative root 2. So this ends up becoming just negative 2 root 2. But if I plug in the negative root 2 into this term, I'll have negative 2 times negative root 2, which is positive root 2. So essentially, if I plug in the positive, I'll end up getting a negative term here. And if I plug in the negative, I'll get a positive term here. So to distinguish that, I'm going to go ahead and say that this is going to be minus plus 2 root 2. To distinguish that if you use the top sign, you would use the top sign. If you use the bottom sign, you get the bottom sign. So there's a correspondence here. There's a link between the two. When you plug in the plus, this term ends up being minus. When you plug in the minus version, this middle term ends up being positive. So there's this opposite correspondence, and I will signify this opposite correspondence by flipping the signs. So you have to always match the top signs together. What happens here? Well, regardless of whether we use the plus or the minus, when we multiply two pluses, we get a plus, and when we multiply two negatives, we get a positive. So this term right here is positive, but then this positive term gets multiplied by this negative, so this will always be negative no matter what. So I'm not going to put a plus or minus, I'm just going to put a minus square root of 2 squared, which is 2. times e to the plus or minus root 2. So it looks like this is going to be, after we cancel those, negative plus 2 root 2 e to the e to the plus or minus root 2. Now notice over here, but like we said, e raised to anything is positive. So this being a plus or a minus doesn't affect the sign of this term. This term here will always be positive. Now its value will change, but this right here will always be positive. And 2 root 2 will always be positive. So we basically have positive times negative or positive. So really, the sign of this whole thing only depends on this order here. So clearly, this allows us to conclude that f double prime of positive root 2 is going to be less than 0, right? If we use the top sign, we have to use the top sign. So if we plug in positive root 2, we'll have a negative this quantity. So negative. And f double prime of negative root 2 will end up being positive. So what does this allow us to conclude? This allows us to conclude that, so by the second derivative test, there is a local, let's say, max at x equals root 2. And a local minimum at x equals negative root 2. Remember, this is essentially saying at x equals root 2, second derivative is negative, so this means we have concave down, which means we've got a max. This one is saying concave up, so we're saying a min. So we have a max at positive root 2 and a min at negative root 2. Part B. Find our critical points. So this is 5x to the fourth minus 20x cubed. This exists on the domain of f, so the only critical points arise when this equals 0. We can factor out a 5x cubed to get an x minus 4. So it seems the only critical points are when x is 0 and when x is 4. So we'll take our second derivative, which is 20x cubed minus 60x squared. Again, this exists, but we're not solving this for 0, so that doesn't matter. We're really just going to need to plug these values in to here. So the easiest way to do this, I think, is to simplify this. So factor out a 20x squared, and we'll be left with x minus 3. So clearly, when we plug in 4, we will have this is positive, and then 4 minus 3 is positive. So a positive times a positive is a positive. So f double prime of 4 is positive, which by the second derivative test implies that there is a local minimum at x equals 4. However, when we plug in 0, we end up getting 0 because of this term, which means that the test is second derivative test. So second derivative test is inconclusive, which means we will have to fall back and use the first derivative test, which is just comparing the value of the first derivative. Okay? So remember, here's our first derivative in simplified form. We know what's happening here at x equals 4. We really just need to figure out this. So if we draw our sign graph for the first derivative, so f prime, negative infinity to infinity, We can still label both of our critical points 0 and 4. So we'll have x equals 0 and x equals 4. And we know that the first derivative is 0 at both of those locations. Now we can use some information that we found about the second derivative test. We found out that x equals 4 is a local minimum. So that means the basic picture or shape of our graph is this at x equals 4. Well, that means we definitely go from decreasing to increasing. So the first derivative goes from negative sign to positive sign because we have a local min there. We learned this information from the second derivative test. We can still import it here because it saves us some time. We don't have to plug in a new sample point in here to find out that this is minus. We know this from the fact that there is a local min at x equals 4. So we really only have to worry about doing one sample point, which is nice. We can just do x equals -1 for our sample point. F prime of -1. If we head over here and look at this, negative cubed is negative. So this term here turns into a negative. And negative minus 4 is still negative. So we have negative times a negative, which is a positive. So this is positive, which means our graph does something like this, which means we have a local max right there. So we can say local max at x equals 0. And together we have this one as well. So